Okay. So welcome everyone. So it's my great pleasure to introduce Dr. Sayak, who is an assistant professor in the CS department at IIT Kanpur. So his research focuses on sequential decision making, multi-up bandits, RL and language model alignment. Prior to joining IIT Kanpur, he did his postdoc work at MSRI India and Boston University. He received his PhD from IIT Bangalore and he's a recipient of INE Young Associate Award from the Indian National Academy of Engineering. So today we'll be talking about Nash Regulator Beyond.
Thank you for hosting me today. And today I will focus on some of our recent work on bandit problems, and will specifically focus fairness guarantees in bandit problems. And this work has been carried out with two of undergrad students, Dhruv, which is from IIT KGP, and Nishant, who is from IIT Kanpur. Okay, so how many of you know about bandit problems? Right? So bandits are sequential decision making problems. So you are given k arms, you can think about k probability distributions, and you do not know the underlying parameter of probability distribution. Think about k Bernoulli distributions. Each Bernoulli distribution has a particular parameter. We do not know the parameter in advance. So k arms with unknown parameters mu1 to mu k. This mu1 to mu1, mu2 to mu k is unknown. And out of this, one of the arm has the highest parameter, right? So one of the arm has probably the highest mu k. That means if I draw that arm, right, I'm possibly get higher rewards. Think about this mu1 to mu k are some average rewards associated with every arm, right? So if I draw a particular arm, say 1, so I'm going to get a Bernoulli reward with mean mu1. I draw an arm 2, I get a Bernoulli reward with mean mu2. And obviously, since we do not know then this mu1 to mu k in advance, we do not know which arm is the high.
It's a stochastic setting.
It's a stochastic setting. Which arm will give me the highest reward? Okay, so there are k arms with unknown parameters. And some applications of this. Have to do this. Yeah. And there are several interesting applications. The first application dates back to 1933, which has been designed by Thompson. And this is on drug trials. So there are k drugs. So out of that, one drug will probably be useful for a particular disease, right? And these k drugs will be administered among capital T number of patients. So the patients will come sequentially, one at a time. Right? At every time a patient comes, one out of these k drugs will be administered to the patient, and the outcome will be received. And depending on the outcome, for when the next patient comes, a different drug or the same drug probably can be administered. And the goal will be to find, after this capital T number of interactions with the patients, to find the best possible drug. Right? So another example is, which is a modern example, is displaying ads. Right? So we log into Amazon, right? And depending on our browsing history, some ads are shown to us, right? So K ad will be shown to us, and we'll probably go and click one of them, and we might not also click one of them. And depending on the feedback the Amazon system received from us, so they will show which ads to display in the next round of interaction. So they have the same goal. So there are T users who are coming, and so the goal will be to, after this capital T round of interactions, figuring out which is the best ads to display. Okay. So here, okay. So the learning proceeds like this. So you have this k number of arms. Say first round, pull arm randomly, pull arm, and we'll get to observe a reward y1, which is drawn from the Bernoulli distribution associated with this arm 2. Right? So y1 is coming from a distribution with mean mu2. Okay. Seeing this reward y1, the algorithm decides which arm to pull next. Okay. Say it decides to pull the arm 1. Okay. And then it observes the reward y2, which is drawn from the associated Bernoulli distribution of arm 1. Now, seeing these two rewards, y1 and y2, the algorithm now decides which arm to pull next. Say it pulls the arm 3, and obviously we will get a reward which is drawn from the for the part from the probability distribution of that particular arm. So the learning goes like this in a way, and similarly you can think like the fourth round say algorithm draws arm 2 and get to observe the corresponding reward, and the learning goes like this for capital T number of rounds, and at the end the algorithm's goal will be to find the best arm. Okay.
Is this base term identification
No,
or you want to
I'm coming. Yeah.
Okay.
Find the best term. Okay, so here is a formal notation. So algorithm has access to k distributions. You can call each distribution as arms for t rounds. Each round small t in 1 to capital T. Algorithm selects an arm I sub t, which will be any of the k arms, and receives a random reward. So the expected reward that the algorithm will receive at round t, which will be the expected value of the mu of the drawn on IT. So the expectation here is over the randomness of IT. So each IT could be a random variable depending on the random rewards that the algorithm has received before the round t. So IT is a random variable depending on the past history, randomness of past history. This expectation is over the randomness of IT. So this is
the obvious that it is expectation of mu of IT instead of generally it is expectation of x of IT, right? So x is the reward that you get for the Bernoulli raw, and then IT is the index that you pull. So is it like obvious that it is equal to expectation of mu of IT?
So here in this notation, this expectation is only over the randomness of our IT.
Yes, so the mean is the mu is fixed, right?
Yes.
But these two quantities could be different.
So you can also have both expectation, another expectation of y of IT. Right? So
that's what I mean.
That can be done. If there will be another expectation, then the first expectation will be the randomness over y.
Yeah, but these two quantities are different. Could be different.
These two quantities could be different. So could be different. So if I take expectation over another expectation of
but IT is okay, but
so if the rewards are generated fresh, then they are the same.
Yeah.
The rewards are independently generated from each draw. So for that case, these two quantities are same. So here, this you can see, right? The mu of IT is basically the expected value of y of t, right? Of that particular round, right?
What was so the IT doesn't depend on x. So okay, so you can it is independent.
Yeah.
Right.
So
then in that case, okay.
So the question was, there is a random reward, right? Which is y, right? So this expectation actually, what I have written is not over the random reward, right? Because that I have already subsumed in mu of IT. The mu of IT is basically expected value of the random reward at round t. So the question was whether these two quantities are same or not. The answer is yes, because once the IT is fixed, once the arm that we choose is fixed, right? The random draws are independent, right? That's coming from that particular.
Yeah, ID is like the ft minus 1 measurable, and y that quantity is independent.
So that's the expected reward that we get. And I'm mentioning that our goal will be to, after this capital T round of interactions, to find the best arm, right? So related metric is, this. Okay, so and find the best arm, and the benchmark is defined like this. The benchmark is the best arm, the arm which has the highest expected reward, highest mu, right? Finding that best arm, right? And the highest value of the expected reward is mu star, which is the maximum, the mean, right? The goal will be to somehow find the arm I, which has the highest mu. Okay, so related metric considered in the literature is something called regret. This regret is the difference between the benchmark and the average expected reward that we are going to get, we are getting for what the capital T rounds. Okay, so why it's a related metric? Because if we can ensure that this value is very small, right, close to 0, right, that means average expected reward will be close to mu star, right? So on an average, we will probably have identified the best term. That's why it's a related metric. And why it is called regret? Because we do not know the benchmark mu star in advance, right? So this is a regret of not knowing the benchmark mu star in advance, and the price that we are going to pay, but of not knowing this of mu star is this quantity. This is a regret. Okay, and the goal will be
Just to be clear, like it's not just that you don't know mu star, you don't know which arm gives you mu star. Like even if I give you mu star, that would not be.
yes, exactly. We do not know mu star. We also don't know which arm gives.
Give me mu star, right? That will help me because I can just estimate from my past experience. So this problem.
No, but you need to know what arm is going to give you mu star, right? I mean, like if I told you that the best arm is going to give you value equal to 1000, I still don't know which that arm is, no?
Yes, that's true.
But you're saying that somehow.
But I'm saying that the problem becomes easier, right? If you have additional information, the problem becomes easier, especially in the. For example, I know that for a fact that in the adversarial setting, without this thing, so if you know that there is an arm that gives you zero reward, zero loss in the loss setting, then the regret can be made constant instead of square.
That I agree. Okay, right. So it's not clear what.
So here, if mu star is given, right, we can do a initial round of exploration and find out which arms means, right, estimated means are close to mu star, right, and then eliminate based on that. We can do elimination procedure.
So you can get potentially better regret, right?
Yeah.
You see.
Maybe
Should be
possible.
possible.
Maybe constant.
I still don't see it. Like in the sense that suppose it was the case that the arm that gave you mu star was the last arm or something. I mean, like, how is this better? I mean, I don't know if this is a complete tangent to what Chayak wants to talk about, but
Maybe we'll do this later. I guess.
yeah. Okay, let's take this up later. Yeah.
Okay, so this is the metric that will be our focus, minimizing the regret. It is also called average regret because we are taking the average reward, average expected reward. All right, the classical algorithm which minimizes this regret is the so-called UCB or upper confidence bound algorithm. It has been done like 20 years back. So say that by round T, arm I, a particular arm I is sampled say Ni times and has empirical mean mu I hat, right? So you are collecting Ni samples from its distribution and computing the sample mean. And we can define a UCB estimate like this. We just take the sample mean and add a inflationary term with it, which is inversely proportional to the number of times it has been pulled. That means if an arm has not been pulled enough, right? That means Ni is very small, we'll artificially bump up this kind of confidence bound estimate of that particular arm so that it will be pulled in the next time because it has not been explored enough, right? So we don't know much information about this arm, right? So let's do some incentive so that it will pull in the next time. But suppose if some arm has been pulled enough number of times, then this second term, right? Second term is small enough, right? And this UCB is governed by the sample mean, which we can expect, right? If an arm has been pulled enough number of times, this sample mean by law of large numbers are close to the true mean. Right? So this is the UCB estimate. And here is the pictorial representation at some point of time during the learning process. So there are k number of arms. We have computed the sample means of each arms, mu1 hat to mu k hat, and we just put a envelope around the sample means, right? The width of this envelope is what the UCB index is, what the confidence with this, right? The square root of 2 log t by Ni. So the algorithm is simple, right? And so we compute the UCB index. And why the UCB index work? Because the choice of width is coming from the Houghton inequality, which tells that if I choose the width like this, then my estimated mean will be bounded away from the true mean, right? If the bound is greater than epsilon, then the probability will decay exponentially with this bound, right? That means if number of samples which I collect for that particular arm I is high, right? So this probability will be very small, right? And this quantities mu I and mu I hat will be very close to each other, and that means we have a good enough estimate. Okay, and this has been a standard Houghton bound will work because the samples are independent, right? Samples generated are drawn are independent. And the algorithm is simple, that we just select the arm IT which has the highest inset. That will select the arm which has the highest mean plus this confidence term. That is a simple algorithm. It is optimistic algorithm. We're always been adding a confidence term with the sample mean. And this algorithm does very good. It achieves this order of square root k by t degree. So what does this tell? That if my t is high enough, right, this term vanishes down to 0. Right, that means we are able to go close to mean star, the benchmark. Right? Obviously, number of arms also play a part in the regret. If the number of arms are high, the regret will be higher because it will be harder to distinguish between which are the. Okay, this is a simple algorithm. It works fine for this particular problem.
So this does not depend on the variance of. So we just know the mean of the distributions, right?
Yeah. So here the assumption is the variance is. So in this figure, I've assumed the variance is 1.
for all.
Yeah. For all the thing, the variance is 1. Think about Barnum, right? Or a constant.
So following up on that question, are you assuming that the distributions are subgaussian or something?
Yeah, I'm in this case, you can think here, I'm assuming distribution are 1 subgaussian. Okay, that means subgaussian or Gaussian variance. Think about one only.
Or I'm going to use this for things.
Huh?
So you're going to use this.
Use this housing or reward bounded between 0 to 1. Any bounded random variable between 0 to 1. I'm just assuming this. So if it was a sigma subgaussian, the regret will be just scaled by sigma. Just add a sigma to it. In the sigma index also multiply by sigma to it. Alright. So now let's think about algorithms for decision making in practical world. So now we're focusing on minimizing the average regret or maximizing the average utility across T agents, right? So there is one problem which comes here is that same average reward can hide which agent benefits when. Consider this picture, there are T number of patients coming one by one. So we can fix a particular amount of average reward in advance, that this is the amount of average reward we want to achieve, right? We can possibly achieve that average reward, but by giving very low reward to early patients, right? And high reward to late patients. We can fix an amount that can be achieved by giving low reward to early patients. So what does that mean? That means the early patients, the drug that was administered to the early patients, which will not be helpful for them, right? And they would suffer. Obviously, the late patients will get high reward. So we are achieving for a square root T regret. So that means we can, for first square root T number of rounds, we are allowed to make mistake, right? Full mistake, right? Zero reward, right? That means first square root to T patients will get, the drug will not work for them. The rest T minus square root to patient, drug will work for them, right? So this doesn't work in every possible scenario like clinical trials, right? So first square root patients will not receive the particular good treatment, and that will suffer them. And that actually is problematic in social welfare settings, where we care about the entire society will get benefited from the exercise, not only a particular section of the society.
So are you saying that since it's an aggregate regret, there's only the sum of up to t equals to 1 to capital T is square root T.
Yes.
So you want something much more finer control, right?
Exactly.
But these kind of things have been studied. This is called adaptive bounds. I mean, for any interval bound, so interval regret of length I, you have a regret of square root of I.
For even for the first interval,
For any interval of length I.
Okay.
For any interval of length I, you have a regret of order of square root of I. And this kind of algorithms are known in the OCO setting, in the full information setting.
Okay.
These are called interval regret. This particular quantity is called known as interval regret, and yeah.
I don't know about
different
this.
variants.
Yeah, we might talk about
Okay,
it.
sure.
I don't know about this line of work.
Okay.
Yeah. So we want a social welfare setting, and for that we want a metric which ensure fairness by design. That means not all the patients will get some reward. Not that first early patients will suffer from low reward and only the late patients will benefit. We want a social welfare setting where all the patients will get some amount of reward. So for that, we need to develop some metrics, some regret metric or some reward metric based on the collective welfare of the society. Think about the standard setting of social welfare where the wealth will be distributed, not possibly equally, but distributed well over the entire society, right? So the poor person in the society will also have some amount of wealth. It's not a capitalist setting where rich has the most of the wealth and the poor doesn't have any wealth at all, right? We're in that kind of a setting. And this has been well studied in fair allocation. I think Umang has worked on this kind of problems, fair allocation, fair fair division literature. Some Nash social welfare metrics have been studied in this fair allocation and fair design literature. And in Bandit, Professor Siddharth Burman's group from IICA started this study around 2023. They brought this concept of Nash social welfare in the Bandit setting, where we need to quantify a Bandit algorithm performance using this Nash social welfare metric. I'm going to talk about this metric in a while. So the idea here is to ensure that all the patients, right? All the patients get some amount of it. Not the first, all the patients is very heavily penalized. That's the idea here.
Question.
Yeah.
So maybe I'm just missing it. Is there a way to see this problem as a bandit's problem?
So this problem is a bandit problem is, so there are T number of patients, right? There are K drugs for a particular disease, right? Say COVID when COVID hit, several drugs were getting developed, right? So you need to have some volunteers, right? So first patient comes, you administer one out of 10 seconds, right? See whether it works or not, right? Based on that, suppose it doesn't work, that means that patient is not treated, right? So he becomes a victim, right? And based on that, do a follow-up. Okay, so let's focus on the Nash social welfare. So there are T agents. They have values V1 to Vt. So in our case, think about values are expected reward, right? A welfare function takes this sequence, which are positive numbers of length T, and gives also scalar value, which is also positive number. That's a welfare function. So one welfare function we have seen, which is the average of these values, which is called social welfare. Just take the arithmetic mean, right? The another extreme case is called something called egalitarian welfare, which is take the minimum of the valuation, right? This welfare is telling the poorest person in the society will also have good amount of wealth. But social welfare is telling that average wealth is in the society is good. Think about a GDP, right? A GDP high of a country doesn't mean that every section of the society has high GDP. Something in between is called Nash social welfare. Instead of taking the arithmetic mean of the rewards over the round, take the geometric mean of the rewards over the round. Right? Now consider the case if I have the valuation or the reward 0 for earlier number of early rounds, right? This social welfare will go to 0, right? However, the arithmetic mean will not go to 0, right? It will have some value. So this social welfare will prevent that kind of things from happening, that the earlier rounds will have 0 welfare. And as it turns out, this welfare sits perfectly in between these two. This inequality is obvious by definition, and this comes from the AMG movement. Okay. So consider this case. So I have T number of agents, and half of the agents, first T by 2 agents have 0 reward, and next T by 2 agents have half reward. The social welfare is same as the following setting, but all the agents are 1 by 4. Right? In both the cases, social welfare is same. Even if the first half has 0 reward in this case, right? But Nash social welfare prevents this. In the same setting, the first part where the half of the agents have 0 reward will have social welfare, Nash social welfare 0, which is always less than the second case, right? That means in this way, Nash social welfare prevent for this kind of things to happen. That the first initial rounds will be heavily penalized. Right? Those kind of things will not happen. It also has some nice properties. It satisfies a principle called Pigot-Dalton inequality aversion principle, which tells that we are doing a Robin Hood transfer, taking epsilon amount of wealth, very little bit of epsilon amount of wealth from the rich, and giving that wealth to a poor person. Right? The wealth in the system remains same because I'm just taking epsilon from one and giving to another. But what will happen if I do this? Social welfare will remain same, but Nash social welfare will increase. If I take some amount from rich and give it to poor, the Nash social welfare will increase because of the concave property of log. Okay, so this is called Pigot-Dalton inequality aversion principle. Nash social welfare satisfies this. It's also invariant to individual risk scaling. Suppose someone reports, instead of reporting their actual valuation VT, I multiply with some number 100. Everyone multiply some different numbers and report that value, right? So what will happen if I just multiply a constant CT with every VT, right? The constants will come out, all the constants together, and the product term will come out, right? But that will not happen here, right? Constant will sit inside, it will not come out, right? So what will happen? So even if someone just misreport their values, right? Or instead of reporting $1, reports 1 rupee, the ranking will remain same in this Nash social welfare. However, that doesn't happen in social welfare. If someone reports, instead of their value $1, reports $100, probably you're going to select that person, right? You're going to put that up. So this is individual to invariant individual rescaling. It is also symmetric, right? If I just change the order, it will not change. Right? So nice properties it has. And it turns out that this is the unique social welfare function. This Nash social welfare is unique social welfare function which satisfies all these three principles: Pigot-Dalton principle, individual rescaling, invariant, and symmetry. So that's why it has been studied in economics, in econ CS literature for long, in different problems, allocation, fair division problems. And recently, with Professor Burman's group, have started this one in the Bandit setting. Okay, so now, using this social welfare function, we can now modify our regret definition. Instead of the arithmetic mean and taking the arithmetic mean subtract from the benchmark, we take the geometric mean and subtract from the benchmark. Now our goal will be as same as the previous. We need to minimize this regret as low as possible. So possibly we want to achieve the same regret scaling that we have achieved here.
So what is the argument for taking the expectation inside? I mean, it should be expectation should be outside, right?
No, so this is a expected reward.
No, I mean this one, right? The right hand side.
This is expected reward. This is the expected reward at round T. I'm taking the product of this.
Yes, but we care about the whole reward, right? The entire reward for the entire horizon. So we should take the expectation at the end.
No, I'm just talking. This is the expected reward at round T.
This is expected round, but we care about the total cumulative reward, just like in regrets.
So here also, see, you can see the expectation is inside the sum.
Because of linearity, but it's not linear, right? I mean, at the end, care about whatever is the total reward that you get, or total utility that you get at the end of horizon.
Total expected utility. So this is the total expected utility that we get. This exact quantity is the total expected utility. Think about, I'm taking expectation for each round, right? I get this much of expected reward at each round.
The formula for the social welfare is this, right?
This.
So I should take expectation outside, right? Expectation of product of VT.
So V is my expected value of Vy. VT is my expected value of that of.
Oh, so this is not the actual reward that you get.
This is not the actual random reward that I get. I'm getting this is the expected value.
But we have concentration that shows that these two are kind of close.
This bound is only for this. We do not have that.
I think if you put expectation outside, it might be zero for most exactly.
Yeah. So if we one point is if we put expectation outside, if one of them becomes zero, right? right? It might kill. Like one of the random bit becomes 0, right? If I just take the random,
there is no hope for proving anything. Sir.
yeah.
No, but don't imagine that the high probability none of them will be 0. I mean, let's say they're all like.
Yeah, but there are concentration.
But one, like if I just work with random rewards, right? Work with random values. One sample can be 0.
But let's say your random values is a uniform distributed between 0 and
True, true.
right? So then obviously you already run them to 0.
Yeah.
I mean, the arms are fixed. Okay, so they could have 0 removes.
So there could be sample paths where it will just collapse.
Yeah, in that case,
But
we have
maybe the sample path will be very less in problem.
So do you assume that the expected reward for all arms are strictly positive?
Yes, exactly. So here is the assumption now. So the geometric mean will be defined, right? Only for positive quantities, right? Non-negative quantities, right? So the assumption is the expected mu, all the mu i's are positive, greater than or equal
You
to
don't
0.
need that assumption.
To define geometric mean, I need the bts to be non-negative.
And then like to get a good bound on the limit, you don't need that.
So for get a good bound of the average degree, you don't need that.
No, it's not the average limit. Even for the Nash.
Yes, because to define geometric means, I need that. I need the VTs to be non-negative.
VT is minus.
VT is the negative, not defined.
No, I mean, not minus, but I'm saying non-negative.
Yeah.
I thought that what you were doing was that IT would not be, even the initial bound would not be fixed. You would randomize over some set and therefore you would get the.
Yeah, but the mean of IT, right? This is the mean.
Yeah, so surprise.
That cannot be negative.
What negative can be zero.
So it can be 0.
Can be 0, but it cannot be negative.
If it is 0, then
If
you
it is 0, then-
exclude that arm at least once.
But random.
The randomizing.
So average reward in that expression would be opposite.
So, but you might as well have a dummy arm, right?
No, all I am telling that mu i's, right? Mu i's has to be non-negative. Just to define the necessary qualifier function.
Non-negative is fine,
Yes.
but it could be zero.
It could be 0. Mu i's could be 0.
Sure, sorry, yeah.
Mu i's could be 0.
Yeah.
So another question that the regret that you defined here, so the normal regret. So this is pseudo regret. This is not
Yes,
the actual.
this is pseudo regret.
So if I consider the actual regret in that case, you have to take expectation outside.
Yes.
In that case, we don't have any.
No.
But here,
Here you have
any bound instead of regret concentration gives you.
concentration bound you have, high priority bound you have.
So
Here you do not have any.
you need new tools.
I do not know whether it is possible or not, but you need new tools. So this definition is only for expected values. Okay. So as we can see, right, so Nash regret is always higher than the average regret. So it's a tough quantity to minimize. Right? It's always higher than the average regret. Then it's a tough quantity to minimize than the average regret. Okay, so Berman et al. Showed that the following algorithm works very good. They showed that instead of taking UCB, I take something called Nash UCB. So Nash UCB differs from UCB in the following sense. So we have the same sample mean, and in the confidence width, we add multiply by the sample mean, square root of the sample mean, right? So the confidence width, it becomes sample mean dependent. They are called Nash confidence bound. And they run the following algorithm. They run a two-phase algorithm. First phase is just uniform exploration. For square root number of rounds, we uniformly explore. And the second phase, I just pick the arm which is the highest Nash confidence instead of the UCB bound, which UCB algorithm uses. And they showed that simple strategy gives the order of square root k by t Nash regret, which is the same scaling as the average regret, order of square root k by. I'm hiding some log factors, log t, log k factors here, but we'll get the same scale. And these are optimal because the lower bound also exists. The simple strategy. But what made them achieve this is they do the analysis via stronger Hopding inequality, which is called multiplicative Hopding or Charnock bound for multiplicative Charnock bounds, right? For Bernoulli random variables. They use that, which just tells the deviation of the true mean from the sample mean as a function of the true mean, right? It actually goes down with the value of the true mean. It exponentially goes down the value of the true mean. That means the sample mean will be true mean will be one plus minus delta away from the sample mean, right? With very low probability. This is a stronger Hobby inequality that they use, and this is also called multiplicative inequality. So very good. This is very good. But there is a problem here that this inequality only works for non-negative and bounded random samples, random viewers. I'm not talking about expected viewers anymore. Non-negative and bounded viewers, the multiplicative Charnock bounds, right? You know this works for Bernoulli random variables, right? But it doesn't hold for a Gaussian rewards. So rewards are drawn from a Gaussian distribution, which is a positive mean, right? It doesn't hold for a Gaussian rewards, which is typically or very much used in bandit, stochastic bandit literature. Rewards are assumed to be Gaussian, right? It's a general class of thing, right? General class of rewards. But this inequality doesn't hold for that, right? And so entire analysis fails. So that's the question that we ask, right? What happens when rewards are sub-Gaussian with positive mean with non-negative mean? But the random realizations from the distributions can be negative. Okay, only the mean has to be non-negative. So what happens when rewards are sub-Gaussian? Because we thought that okay, this makes the although results are good, but it makes the problem very confined, right? You can only work with Bernoulli rewards, right? So let's try to expand the horizon.
I was a bit something which is more philosophical question. So I thought the point of defining this Nash UCD was somehow to be fair, right? But we're doing literally the same algorithm, right? It's just like there's some tweaking going on. So like somehow without being fair, we are being fair.
Yeah. Yeah. So the metric is boiled down to the metric. The metric that you optimize is probably fair. Right? That geometric mean, right? We get square root k weight in asterisk, right? That means the geometric mean is close to mu star, right? If capital T is very high, right?
Yeah, but I think I'm not trying to analyze that why is this Nash NCBI more fair than UCBI? I mean, it seems like the same thing. Yeah, this is a new I had to take insight along how that is.
Yeah, I don't have the answer for that. My answer will be to come from the answer. Like the Hamiltonian answer that you get, take t infinity tends to infinity, this goes to 0. That means your geometry mean very close to mu star. That means every time, right? All the events get good expected reward. So it becomes fair. It's a roundabout way of answering it, but I don't know the answer for this confidence weight is fair.
And also, do you have gap dependent nodes?
No. This gap independent. Okay. So with this, we try to answer this question. What happens when the rewards are more general, rewards are sub-Gaussian? And our proposal is very simple. Forget about all this Nash confidence now. Let's work with UCB only. Maybe that relate to you, right? UCB, NCB, what is more fair, we don't know. So our proposal is let's go back to UCB only. Similar algorithm, phase 1. Instead of performing uniform sampling for square root t rounds, we just do uniform sampling for some random number of rounds that we are going to control it later. Second, instead of pulling arm using Nash confidence bound, we pull arms using UCB confidence bound, the simple UCB confidence bound. Okay. And the key, and this is our UCB confidence for sub-Gaussian random variables with unit variance. The key idea here that we use a random stopping rule which depends on the data collection. The phase 1, the random exploration phase, we stop at the first time t when for some arm I, the number of times the arm has been played is greater than this one. Right? It is greater than log t divided by some number, some mu I hat minus square root of by ni square. So what is this quantity? Let's look at this quantity in a bit, right? This is we do not know mu I, right? This is the most pessimistic estimate of mu I we have with high probability using Hobby, right? Hobby tells mu I lies within this band, right? With high probability, this is the lower band, right? This is the most pessimistic estimate we can have at any round using Hawking equal of mu1. Right? So we'll stop only when the number of plays for a particular arm I exceeds this threshold, which is log p divided by its square of its most pessimistic estimate. Right? That means we'll keep on running the keep on pulling the arms sufficiently many number of times, so that we have enough information accumulated. The first time you can ignore, it is just to make sure some algebraic thing that this quantity mu I hat minus this is greater than 0, right? That can be ignored. So how do we get, right? So phase 1 will be run and phase 2 will start once the confidence for each arm is strong enough, right? Once the samples are collected are good enough.
And it's a super question. So, I don't know much about UCD, but so how is it different from UCD?
So difference is that in standard UCD algorithm, right? We do a round robin sampling for k number of rounds. For k rounds, right?
And K still root K.
No, K is also number of
K is the number of rounds. Number of rounds.
And, okay, sorry, yeah.
K is number. We do a round robin sampling for k number.
So K number of arms.
K number of rounds.
Cancel
Each arm once.
and then follow the rule.
And then follow the.
Okay, heavy is giving more time.
Here it is giving more times for some random number of rounds.
But you're stopping to who looks at one arm. You're saying I have sufficient confidence for all arms.
Yeah, for some arm,
For any arm.
it actually.
Some.
Some arm, it actually.
Yeah, so how does it guarantee that for all arms you are winning?
So it doesn't guarantee, it actually basically tells where, yeah. I'll tell you, right? I'll tell you one result.
This term should have this hitting first.
So I'll tell you, so there is this term, this weird play going on. So I'll tell you what this
Phase
is.
1 is uniform, right? So you are just doing it
Uniformly sampling.
So if it holds for any one arm.
Uniform, yeah, so whether we are going to.
So I just want to clarification. So we are working that the rewards can be negative also, right?
Random
Rewards can be negative. So okay. So but the rewards can be bounded? No.
Can be unbounded. Only the minimum has to be possible.
So what I know is that if the rewards are bounded, then also we have a concentration rate named Bernstein inequality, I guess, that gives you some if it's negative, it still gives you some concentrations, right? With variance, I guess. But
Bernstein does Bernstein works for a negative? I'm not sure.
yeah, I mean you just need to so you need to have a zero mean random variable, but I think that could be you just need the the modulus of the random variables to be bounded, that's it.
Modulus of the random variable to be bounded. Okay. Bernstein does, I'm not sure whether it works. Negative.
Yeah, we bound the modulus. But anyways must be as unbounded.
Yeah, it is
Unbounded is here.
Now, Bernstein doesn't work for unbounded variable, but it works for negative.
Okay, so this is our rule, and in phase 2 we just run UCBs, and UCB will give us this, or we show that UCB gives us this square root k by t Nash degree. It's the same bound as the previous, but the now scope has been extended from bounded positive random variables to unbounded random variables.
So your algorithm, okay. So are you claiming it's like a best of both worlds? Because UCB naturally gives it is almost UCB, right? UCB naturally gives you normal linear guarantee like square root t, and now you're showing that the same UCB also gives you.
Yes, with a careful exploration like this.
Yeah, but it is only root t, so it is not going to hurt you, right?
Yeah, so the constants are sitting here.
Yes,
some big constants in the sequence.
Square root t for both integrated as well as this Nash
Would you also get that? Like, does the Nash rate is bounded by the average regret?
Yeah.
The regret, there's no comparison. Absolutely, the comparison. When you take a difference,
so lower bound you can.
Lower bound from now.
Nash regret is lower bounded by average regret.
Yes.
So lower bound follows from average regret lower bound. Okay, upper bound doesn't follow.
Okay. So sorry, one question. So you are considering sub-Gaussian random variables. Like, how bad if we approximate it by some bounded random variables?
Yeah. How bad, right?
Yeah.
So some samples could be very large, right?
What he said.
Yeah, so some, yeah, obviously we can bound and then apply this technique, obviously we can quantify that bound.
Like if some sample is
log t, right?
yeah, you might get an extra log ticket.
It's extra kind of log t, polylog t.
Like
Because
t rounds, all the rewards would with high probability would get most noise.
yeah, so now that thing, right? So what our algorithm shows, here I think probably answer your question. Another is good event, which is basically bounded by with very high probability, which happens with high probability in routing. And under this good event, the length of phase one is always bounded by this two, which is you can think about length of phase one is order of k log t divided by mu star square. This is what we show, right? And why? And there is something like why this bound holds. It holds from our stopping rule. We stop phase one when at least for one arm, right? Number of plays exceed this threshold. And so if the length of phase one is less than this quantity, then we can show that all arms will violate this. So this is a lower bound. This becomes a lower bound. And if length of phase one is greater than this quantity, then we can show that optimal arm will violate this. Okay, so this becomes a upper.
But these are all high probability, but you are claiming it's almost sure it comes. I mean,
So under this good event, this tau is a random variable. I'm just writing since tau is a random variable.
It's a high probability, right? And like,
So under this good event, the random variable is bounded by this two almost shield. Under the good event. Okay.
under the good event is almost sure.
Under the good event is almost sure.
And the good event is high probability.
Good event holds with high probability.
So basically, this is also high probability.
Yes.
What I'm trying to understand, so you have this phase one that has this length now, and you're stopping it at some point determined by your samples. Why can't you, so you have this bound, right? So why can't you always stop it at 512 k log t divided by stress?
U star is not known.
U star we do not know, right? We do not know U star.
So all is going on is mu I hat is known as well as ni is known.
Okay.
So as you proceed, these two quantities have been compared. As soon as for one arm this is satisfied and that. But still it doesn't.
Yeah, still it's, I think I also don't know the exact intuition behind this. The mathematics comes out of this, but I'll think about
So
it.
let me push it even more. So mu star is not known with some constant, right? So why can't I stop it after t to the point one?
T is also.
Then you're determining.
In regret, we will be able to bound it.
Typically we don't want to know T. For log T.
But even if T is not, then we won't be able to regret bound the regret.
Alright, t to the point one I can pull this fair change.
But that then we will not be able to bound the Nash regret if we know
No,
it.
it's still I'm sampling randomly, so why not?
No, because crucial is to ensure that our phase one length is inversely proportional to 1 by mu star square. That is very crucial for the bounding the Nash regret. It comes out to be very crucial. And we need to show that tau is inversely proportional to 1 by mu star square. And that is coming from here. This is basically some kind of pessimistic estimate. So that's the main crucial point, right? We need to show this. Okay, this is first that this lemma tells that we are sufficiently exploring phase one, at least log k log t by mu star square, number of terms. And once we are done with phase one, right? Phase two is very easy. It's so that it's whichever arm which has been pulled in phase two is near to the optimal arm, mu star, with a high probability. Under this good event, if an arm I is pulled in phase two, then it is very close to mu star. Right? This we can show. And this proof is standard. It's coming from UCB rule. That you know, right? If I is pulled at some round, if UCB estimate has to be higher than any other arm, so it is higher than UCB of I star, which is the optimal arm. And obviously UCB of I star is higher than mu star because of the property with high probability because of these holds. And then using the under the good event, we can show that mu I hat plus 2 square root 2 log t by ni is greater than mu star. Because this is UCB of I, mu I hat, this term is UCB of I, which is greater than mu star. This is the first part, and the second part is coming from the good event that each arm's mean, true mean, is greater than equal to the sample mean minus this, right? Because this is your lower interval, right? So true mean has to be higher than the lower interval. So just using the properties of good event and the UCB algorithm's property, we are able to show that any arm which is pulled in phase 2 is near object. So that it will occur, it will have very less contribution to the Nash regulator and high contribution to the Nash social welfare.
It was against the whole concept of Nash regulator. You don't want to maximize on this.
We don't want to, but it is in phase 2, right? It is in phase 2. Phase 1 has been done. That means the initial rounds we have made sure the Nash regulator is not very low, right?
Oh.
Nash social welfare is not very low. We have made sure in the initial round. How? I'm coming to the lemma. So we'll proceed the Nash regret proof in two cases. First case, we'll assume that the mu star is less than square root k by t. That's the assumption. First case. And if this is the case, mu star is less than square root k by t, our regret bound proofs follows trivially because of the regret definition. Just this time I just upper bound, lower bounded by 0. This is a trivial bound if mu star is less than square root k by t. That means small enough mu star. But when mu star is high, greater than square root k by t, then we need to analyze the Nash regret. So we need to lower bound Nash social welfare for that. So we have to upper bound Nash regret, so we need to lower bound the Nash social welfare. So how are we going to do that? We are going to lower bound the Nash social welfare for both the phases, phase 1 and phase 2. And we have to make sure both the phases we have good amount of Nash social welfare.
Basic question now.
Yeah.
Why is mu star the right benchmark when you're looking at Nash social welfare?
So mu star is the mu star is the, it is obviously it is not right benchmark because we are also not completely going, completely discarding the utility, right? We're not.
There is no principal reason to now consider mu star.
No, because we also want to have an algorithm which is effective. We just do not.
Just mathematically the best thing every time you get.
So R Nash is always non-negative.
Yeah, it is always non-negative, and we also want the algorithm to have some use, right? If benchmark is some what benchmark that mu star, the algorithm might have no use, right? We want the algorithm to be of some use.
Otherwise, you could just redefine explanation for the whole time.
Okay, so our Nash social welfare we show that this is lower bounded by this. That means it is not very low. What does that mean? That means the initial round, the expected reward the patients get in initial rounds are also bounded away from 0, right? And this is the mu star to the power tau is the highest Nash social welfare that one can get in first tau rounds, and we are away from that with this quantity which is less than 1. Okay, so it's good enough. Get good enough social welfare in phase 1. Similarly, we also, and this is due to the case that the reason is we are doing the uniform sampling, and due to uniform sampling, we can ensure that expected value of mu by t, expected value of the average reward, so always lower bounded by mu star by k. So that gives us this result that we get a good amount of social welfare in initial rounds also. And in the phase 2 also we get also a very good social welfare. So mu star to the power t minus tau is the length of phase 2. This is the Nash social welfare in phase 2, highest Nash social welfare possible. But we get very close to this, right? Which is obviously less than this, but the factor away is given by this. Right? So as you can see, right, this t is high, right? So this term decreases, and we're going very close to mu star to the power. t minus tau, right? So this result holds due to the sufficient exploration in phase 1. That means we are ensuring that each arm is being pulled at least log t by 1 by mu star square times. We ensure that due to our design. And obviously we have showed that phase 2 arms are optimal. So due to this result holds. So in summary, we ensure that both the results, like both the phases, we have enough Nash welfare, so that the total Nash welfare is good. And particularly in the phase 1, we are not, our Nash welfare is not very small.
Okay, but you get this form and any see the in phase 1, how do you get this?
We get this because of this expected value of mu by t is greater than mu squared by k.
Okay.
And you can just
Then shouldn't it just be 1 by k to the power tau? Like, why do you get this?
no, it will be no, I think we can do some simplification to do this, right?
I mean, I don't see how you get capital T there anyway because
Hmm.
tau is fixed, right? So
No. We will have tau value, right? We will use the range of the tau to do. Yeah, we'll use the range of tau to do this. It's some algebraic manipulation.
And if that's the right question, so if I just done UCB, then we know for a fact that that is bad.
Yeah, this might not happen. This might not happen.
So basically the only issue in phase 1, right? UCB.
Phase 1? Yes. Yeah, only issue is they should be in phase 1. Yeah. If you just blindly run UCB, it has been shown that you will get a very high Nash effect.
And they should go to phase 1. So I can just like extend the phase 1 of UCB. I think that's what is going on here. Just extend phase 1 of UCB until we get enough.
Yeah. Extend the phase 1. That's the idea. Extend the phase 1 enough number of times. Enough number of times for enough number of times.
But like in total, why should that help? Like longer phase?
Longer phase 1 will help just to make sure that each arm has been pulled greater than equal to 1 by mu star square times.
But like if I look at the quantity there, right? The R Nash. So where does it appear there?
Which one?
It is just
Which one?
the definition of your unit.
so the definition of R Nash.
Mm-hmm.
T. So how does the number of times I put in appear here? Maybe this to
This here, right? So from here, you get this, right? So there will be, right, this is a final bound, there will be some sum over all arms, Ni will be there. Now I'll take a Cauchy-Schwarz inequality to get to it, right? There is something going on, right? We'll actually divide this proof into for k arms, right? And for each arm will get Ni there. And I'll take a Cauchy-Schwarz some Jensen's inequality. Okay, so now let's summarize that why UCB works and why NCB doesn't. So what is the key point in our proof that to bound Nash social welfare in phase 2, we need to upper bound this term 1 by mu star times square root Ni by half. This is an algebraic thing. We need to upper bound this. And
we can wrap up in 5 minutes.
Yes, and this actually tells that arms are sufficiently explored. And we need to ensure that arms are sufficiently explored by upper bounding this by half. Some constant less than half. And we can ensure this by making sure that we pull each arm at least 1 by mu star square times. We ensure this in our algorithm. So that we can bound this term by half. We ensure this. But instead, if I follow the previous paper's approach, where they run phase 1 for a fixed square root number of rounds, then this will fail. And to bound this term by half, then we need to make an assumption that mu star is greater than t to the minus 1 by 4. We just put this value mu star t to the minus 4 there. So, but what it will do, right? It will lead to a suboptimal Nash segregation. Because for the complementary case, which is less than t to the minus 1 by 4, the Nash segregation will be bounded by t to the minus 1, which is suboptimal. So, this is the exact result that the Berman et al. Resorts to NCB, right? Instead of NCB, they resort to
Mu star is something fixed, right? It's dependent only on the What knowledge you have, and T is something you can make it long.
So, but we need to assume this thing, right? Only if we have used this fixed square root T number of rounds, only if we use are greater than T minus 1 by 4, then we can bound any of them. Okay. So this is the exact reason
I'm just saying if T goes to infinity, then this is very true.
Yeah, but you don't know how you make this thing because you don't know this step.
So this is the exact reason where these guys they resort to NCB, where instead of bounding 1 by mu star square root ni, they need to bound 1 by square root mu star ni. This is coming from the multiplicative property, right? They need to bound that, and they bounded this by assuming mu star is greater than 1 by square by half. Okay, because for the complementary case, if mu star is less than 1 by square root T, regret is anyway bounded by 1 by square root. Okay, and this leads them to optimal Nash limit, right? This is the exact reason they resort to NCB. But the downside is NCB requires multiplicative Hopton bounds, right? Which only works for bounded and non-negative random variables. So that it cannot be generalized beyond this, right? So we overcome this using this stopping rule, right? This is the entire story. All right. So now this what we just 1 minute we can finish. So there are other notion of welfare which is called power mean welfare. So this welfare is defined by this. So we extend all this, right? And power mean welfare is very general. For defined value of P, we get defined social welfare function. P equal to 0, we get Nash. P equal to 1, we get social welfare arithmetic mean. P equal to minus infinity, we get egalitarian or the minimum, right? So this is the entire range. We can play with the entire range of P to get different social welfare, right? And you can think that P is as a fairness utility law. No, if P is low, right? It's high focus on fairness, right? Egalitarian, right? Every minimum individual has high value. P is very high, very close to 1, it's basically utilitarian, right? So P is a fairness utility norm, and as you can see, high negative P is very hard, right? The fairness metric is very strict, and it will be very hard to minimize that regret, right? For P is high negative is a hard problem. So this has been posed as an open problem, and although there are some works in previous which solve this using some unrealistic assumption, we just showed that our simple algorithm strategy works. Same algorithm, only change the stopping rule. Instead of this, just add something P squared. Just multiply P squared. Where P square is defined by this. Basically, P square, I will take P to be 1 if P is greater than minus 1. That means, which is easy regime. P is equal to P if P is less than minus 1. Mind that P can be negative, minus infinity, right? Very close to minus infinity. And just make this change. Obviously, I need to know P for this because that's the regret metric I have to minimize. And just make this small change. And everything works out. Okay. So you get the regret bound, which is same regret bound square root kt, with some factor now depend on P in the front. And this factor is 1 if P is positive, which is the easy regime. If factor is k to the power P by 2, right, which is polynomial in K, right? If P is less than 0. This tells the hardness. Right? Think about P is very high negative. So this is a very high, P is minus 100, right? So this is k to the 50, right? So regret goes up.
Matching normal?
No, matching normal. So this theorem is there is no free lunch in fairness. So if you want high fairness, you will get to suffer by lots. And but this is an open question also. There is no matching lower bound for P less than 0 regime. For P greater than 0, there is a matching lower bound. And open question is P less than 0, where what is the matching lower bound? Okay. So this is where we stop. Before that, I just want to tell that all these ideas extend, these are some numerical results which shows that things work. All the ideas extend to linear bandit problem where the arms rewards are linearly related with some parameter theta, right? Theta is unknown, right? And it classical UCB algorithm achieves d by square root t regret, where d is the dimension of the unknown parameter theta. Same Borman group have achieved if the same Nash confidence bound algorithm achieve d to the power 5 by 4 square root t regret only for positive rewards and all. And they pose this open problem, can one achieve d by square root t Nash regret? And so they achieve d to the 5 by 4 and d by square root t is the optimal lower bounds. So they pose this open problem for also general Gaussian rewards, and we actually solve that the same idea. Instead of doing Nash UCB, just do UCB for linear bandit problem. Same idea works out. Like a bit surprisingly here also. Same. Right, first phase we'll do some kind of uniform exploration. Second phase we'll do UCB, and we will have a data adapted phase. Stopping rule. The stopping rule also looks similar. And same idea works out, and you can solve the open problem. With this, I stop here. That there are several future directions. What is the lower bound on P means regret? So can we extend it to nonlinear structure in rewards and other bandit problems? And I close this with this following thought. That is, my hypothesis is that you suppose you want to solve some regret minimization problem in bandits, any bandit problem, constant bandit, nonlinear bandit, any bandit problem you pick, stochastic bandit problem, and you have an optimistic UCB style algorithm with you, which helps you to do average regret minimization. You have that. That literature is well studied. Okay, my hypothesis is take that optimistic UCB style algorithm A and design two things: a uniform arm exploration strategy in phase 1 for that particular bandit problem you're solving, and two, a stopping rule using the regret bound of that algorithm A. And obviously, since it's a UCB style algorithm, it will have a Hobdin style bound, right? Use that Hobdin style bound to design the stopping. That's my hypothesis on if we can just mess around this, we can solve get Nash regret for any bandit. So I'm yet to verify this hypothesis, trying for several bandit problems. Yeah, let me know if you want to talk about this.
Any question for Sayak?
So in your whole formulation, you assume that needs are non-negative, right? But the problem doesn't really change if I sort of shift everything to the right, at least for the average regret, and I can shift it and make it non-negative, right? And this could also be done if you change the problem statement by, instead of looking at the values, you look at individual regret. Like you try to minimize the geometric mean of mu star minus mu IT.
Mu star minus mu IT.
Right. So in this formulation, mu's do not
need to be negative. So you are changing the metric now.
Right. And it seems like your algorithm uses that mu i's are positive in a crucial manner.
Exactly. Yeah.
So
Wait, but the geometric mean of mu star minus mu IT is not the same as mu star minus the geometric.
Yeah, it's not. Metric is different now.
Yeah.
I'm changing the problem. Like one word define a metric. So for this formulation, it's arguably cleaner in the sense that mu is need to be non-negative. Do you think similar algorithm will work?
Yeah, to check. I don't know. I cannot comment that.
If you just take the log, right? It's a product of this thing. So probably what you're proposing is a product of this. Take the log, then it's same.
Log has the issue, right? If you just take log, right? Mu star values can be, if it is between 0 to 1, then log can blow up.
Yes, log can blow up, but there are algorithms that gives you, it's a EXP concave function, right? So that gives you, better bound than square root 3. Is a rule. Of course, this has to be non-negative for it to be defined. But then it kind of reduces, assuming all this regularity condition hold, then so yes, separate problem, right? Same thing.
But how are you going to get around the blow up?
No, assuming that it doesn't blow up.
Okay.
Because Houston is always starting.
Assuming it doesn't blow up, then
Houston is always starting on mu. It's not going to blow up, right?
No, but it can be between 0 to 1, but very close to 0, it will blow up to negative, right?
But I think this is generally not an issue. It is non-zero because only Newton's step this algorithm. So we know how to actually minimize the regret of log of R transpose X, sum of this, right? And I don't think it assumes anything beyond non-negativity. So this algorithm is only Newton's step, so you don't need to add any epsilon to this. The same, you run the same algorithm and it will minimize, it will give you log regret. Yeah. But it is in the OCL setting, the full function. But I think the problem is invariant variances or bandit.
One thing about yours is I think it's depending on your bit you start with the rate is 0 to 8 bigger. Because you multiply the instruments.
Yeah, that's it.
Okay, so any other question? If not, let's finish that one.
Just do that one. And the one. And right.
No, end the Zoom.
And then leave it. Right?
No, remove this.
Okay, yes.